Thank you, everyone, for attending our first talk. Up next, we have Cody from the ZKEVM team, and he'll be talking about the road to ZKEVM scaling.
All right, thank you. So yeah, I have my slides available here through this QR code. If anyone wants to follow along in that way, there are some links that are possibly interesting, references at the end. And yeah, as the introduction said, I'm a member of the ZKEVM team at the Ethereum Foundation. I'm working more narrowly on like the security aspects of the project, but I want to present more broadly on the project and then focus a bit more on the security roadmap. So to just set the stage, like ZKVMs allow us to take advantage of a certain asymmetry where you can have like low power members of a network checking the work of very high powered members of the network using not all that much data. And so our goal is to scale Ethereum using this asymmetry by having the attesters start to verify proofs that are produced by provers who have big computational resources. And the switch will also allow these attesters to keep low resources, both in terms of the compute that they have and the amount of data that they need to receive to do that work of checking. So here it is a bit in pictures. So sort of prior to ZK, and this is a cartoon, there are things missing, but prior to ZK, what we would have is just the sort of middle section of the diagram here without the prover and the VM. So you would have an EVM implementation that processes a block and updates the state of the system. And what happens with ZK EVMs is that you have that EVM implementation running inside of another virtual machine. Here I say that it's a RISC-V virtual machine. That's a choice. It's quickly become the canonical choice, but there are other possibilities. You'll hear about some of them today, shortly. And what happens in the ZK setting is that you have this VM running inside of a prover who observes the execution of that machine and then produces this green block, this attestation to the execution, which is the proof. And then the attester only needs sort of summary data, so hashes of the trees and of the block to check the update was correct. And I just want to say explicitly that there are proposals about changing the EVM to use some other model, maybe a RISC-V machine, and those are not related to what our team, they're related, they're potential optimizations, but they're not something that our team is working on. They're not part of our more immediate L1 scaling goals. There are optimizations where you could imagine that sort of the blue box, if it's more similar to the enclosing RISC-V VM, then you'll have some efficiency gains. But yeah. Okay, so ZKVM versus ZKEVM. A ZKEVM is just a combination of a choice of a ZKVM and then a program of the blue box, the EVM implementation that runs inside of it. So here are two screenshots of Justin Drake talking about each kind of thing. He tracks carefully what options are available. On the left, these are both from YouTube videos. You can find these links in the blue, where he tracks some existing guest programs and some ZKVMs. And a priori, any combination of these could produce a ZKEVM, though there are technical challenges, which Guillaume will speak about in the next talk. So how will we ship? Well, okay, this is a huge change, and we need to be very careful. So we're going to do it in two phases. The first one we call optional proofs, where the attesters continue to do the normal work they had done up until now, but they do this extra work of checking these proofs, which need to be produced. So this is a trial period. We can see how the network performs, make sure that we do have 100% real-time proving, and respond to bugs. And because it's optional, we can't increase the gas limit. If we did, then the re-execution that the attesters are doing would start to break down, and we would have centralization via increasing requirements. So we don't want that. Eventually, once we're happy with how things look in optional proofs, we can start to increase the gas limit and by doing so, make it required to increase these attester requirements, or that's not what we want. What people will do is just rely on the proofs. Right? So at that point, if the proofs disappear, the network can't function, but we can increase the gas limits. So here's a concrete proposal. Right now it's very basic, it's in draft form, but this is the EIP for optional proofs, and you'll see in my references at the end a link to this, and also a link to the ongoing work actually in the consensus layer specifications, fleshing all of this out very carefully. So who's shipping? Here's a list of a bunch of stakeholders, and we're organizing around this GitHub organization, which is called we call it ETHACT, Applied Cryptography Team. There are 20, 30 repositories in that organization where we are building like universal prover execution framework called Array. We have the planning repo I'll show you where we discuss the plans for the shipping optional proofs. Test monitoring I'll show you, standards for the provers, a lot of stuff. And we have really robust discussions and try to get widespread rough consensus about these things and make them official through pull requests in the repositories here. And we also have, as of last week, a breakout call where we're discussing all of this. And I will show you some things that I presented there. Here's what the planning repo looks like. Here's our list of plans. Project 7 is the security plan that I'll address, but there are many other important aspects of the project, like prover incentives that I won't touch on. Here's we have a channel in ETH-R&D Discord where we're also having discussions, maybe more preliminary to the proposals that go into ETH-ACT. These are all posts from yesterday. And you're very much invited to join us there in these discussions. So here is what I presented last week. I made a basic roadmap in terms of security for the shipping of optional proofs. It proceeds in these phases, which I will now dig into a bit further. So phase 1, we have these kind of 4 first shortest bars are basically, they're solved problems, but it's good to put them down in one place in ETH-ACT. But we've put forward like CapEx requirements for provers, what's a reasonable number of GPUs and power consumption to say that provers should have in order to produce the proofs for the network. We have cryptography requirements that have been articulated in blog posts. So most of this stuff is done. It's just maybe it's good to kind of defragment the discussion a bit and put it down in one place. So that's that. And then these longer bars here, we need to be more precise about the level of testing that is prudent and necessary for optional proofs. That'll be a lower bar than mandatory proofs where we need to be extremely high bar for security. And similarly, part of understanding these systems is having good specifications. Right now, the landscape of specifications is not great. Things have moved very fast. The engineering kind of pushed beyond the careful specification. I think that's acceptable, but now we need to make sure we have very good descriptions of the ZKEVMs so that they can be analyzed by cryptographers and other cryptography engineers. So that's, knowing exactly what the right way to write these specs is something to discuss. The next 2 bars we have are from the cryptography research team at the EF. So they've made something called SoundCalc for precisely describing the number of bits of security that these ZKVMs have. There were conjectures that were in use, and just generally speaking, it's not all that simple to know exactly how many bits of security, but we need to know that we have very high quality security. So that'll be, and by the way, the bars here are sort of roughly temporal, like each vertical slice, is something like a month or a month and a half. I had to be a bit fuzzy because there are some already established deadlines for things, and there are also more fuzzy aspects of this. But this is, reasonably temporal, I would say. So here we're saying, in the next basically month or two, all this is done. The sound calc integrations are done, so that the ZKVMs have given us all the information we need to know that they have sufficiently many bits of security, or at least that we know how to track their bits of security. Because then we, excuse me, we ask then that they have 100 provable bits of security rather than conjectural bits of security, and smallish proofs, 300 kilobyte proofs, by a specific deadline that was published by the cryptography research team. And then these final phases, we need to be very precise about, or at least very thoughtful about how we're going to make use of diversity of these provers, because, sorry, we'll have multiple verifiers in the clients to be sure that a single prover failure, a bug, doesn't bring down the network. So we want to make sure that we have a diversity of software dependencies between, not all the same compiler, not all the same VM, not all the same guest program, that kind of thing. And knowing what the right balance is, there is something that we need to have a good discussion about. Also, criteria for including a given ZKEVM, we need some rough consensus on that. And we also need to make sure that these hardware requirements are reasonable, and that the performance we've seen on ETH proofs is something that we can reproduce. It's not specific to a particular setup, for instance. Hard to reproduce. So then we have that. Here are some pieces of work I've put in on this first phase. So I have this test monitor that checks for compliance with the RISC-V standard for these ZKVMs. They support different targets, and they have different degrees of support. It's still a bit custom. We have a precise specification of the target requirements that I'll integrate, and most of these would meet that. And I also have some starter specs. So I've been using AI to create starter specs, executable specs even. So these are backed, like this is derived from a Python specification, and it's backed by real test vectors that are extracted from the C++ Python or C++ prover library. So it's just kind of a starter to get something down that maybe some of the teams could use to provide these specs in a short time frame. And I have only half a minute, but in the next phase, we need to implement testing, we need to build monitoring, we need to do this specking work, we need to increase the security to the canonical 128 bits and reduce proof sizes. And then we need to do kind of incident response planning, reviewing of all of the specs, and stability monitoring before we launch, where we aim to launch in Hegata. So that is the end. Thank you for your attention.